My name is Omid Sani. I'm a postdoc in the Shanechi lab at USC, and I will be presenting our work on nonlinear modeling of behavior-relevant neural dynamics using RNNs. Modeling of how behavior is encoded in the nonlinear dynamics of neural activity over time is a central problem in neuroscience. Such an encoding model describes the transformation of neural activity to behavior, which consists of four main elements: the mapping from neural activity to latent states, the dynamics that describe the temporal structure of the latent states, and the mapping of the latent states to behavior and potentially to future neural activity. Any one of these elements could be nonlinear, so an important challenge is to learn models that capture nonlinearities and can dissect the origin and type of these nonlinearities, while also dissociating behavior-relevant neural dynamics and preserving them. We've developed a new method termed RNN-PSID that addresses all these goals. RNN-PSID learns the dynamical transformation of neural activity to behavior with an RNN that has an interpretable parameter corresponding to each element of the transformation. Given the training data, RNN-PSID learns all model parameters while being able to set any combination of them to be nonlinear. That is, each of these four parameters can be a linear matrix multiplication or an arbitrary nonlinear multilayer neural network. RNN-PSID also enables causal decoding and works for data with or without a trial structure. For more details on the method, please check out the preprint. We used RNN-PSID to investigate nonlinearities in spiking and LFP activity in monkeys performing 4 different behavioral tasks, and found strikingly consistent results across all 4 of these independent datasets. First, across latent state dimensions, nonlinear RNN-PSID enabled more accurate behavior decoding than other methods, including linear preferential methods and nonlinear non-preferential methods. These results suggest that RNN-PSID learns the behavior-relevant neural dynamics better due to its nonlinearity and its preferential learning of these behavior-relevant neural dynamics. When also considering the prediction of neural data, RNN-PSID achieved the best description of both behavior and neural data overall across all datasets. To see how accurately each model describes behavioral and neural data, in addition to the behavior decoding accuracy, in each model we also computed the accuracy of neural self-prediction, that is, predicting future neural activity from past neural activity. These two performance measures are shown on the two axes of this plot, with the points towards the top right indicating models that describe the neural behavioral data the best overall. And for both RNN-PSID and for non-preferential nonlinear modeling, denoted by RNN-NDM here, we selected the best type of nonlinearity for each model parameter by searching over various linear and nonlinear networks and picking the best one based on the training data. In all datasets, RNN-PSID was always on the best performance frontier of simultaneously having accurate behavior decoding and accurate neural self-prediction. In other words, describing the neural behavioral data the best overall. We next used RNN-PSID to dissect nonlinearities and find their origin. Surprisingly, while nonlinearity could be in multiple elements of the model or could be different across datasets, RNN-PSID found that consistently across all datasets, behaviorally relevant neural dynamics could largely be explained with nonlinearity just in the behavior readout. We compared models with different nonlinearities and found that the behavior readout parameter CZ was largely sufficient for describing the data overall, reaching the best performance frontier of having both good behavior decoding and good neural self-prediction simultaneously in all datasets. And these results not only held for spiking activity, but also held across other neural modalities, with RNN-PSID again significantly outperforming linear models and non-preferential nonlinear models in this decoding behavior and also in explaining the neural behavioral data overall, and with nonlinearity in the behavior readout parameter again being largely sufficient for explaining the data also for the LFP data. One notable result was that raw LFP benefited the most from nonlinear RNN-PSID modeling, and even outperformed the spiking activity in some datasets. This suggests that with its flexible modeling, RNN-PSID automatically extracted nonlinear transformations in raw LFP activity that achieved more accurate decoding of behavior than traditional pre-specified LFP features such as power in different frequency bands. For more results, please check out our preprint. Taken together, RNN-PSID provides a general new method to model and dissect the origin of nonlinearities in neural data while dissociating and prioritizing the learning of behaviorally relevant neural dynamics, and also enabling causal and computationally efficient inference. It also works on data both with or without a trial structure. Across multiple independent monkey datasets with a diverse array of behavioral tasks, brain regions, and neural signal modalities, RNN-PSID discovered a strikingly consistent origin for the nonlinearity in the dynamical transformation of neural activity to behavior, and more accurately predicted the neural and behavioral data overall. With that, I would like to thank my advisor, Maryam Shanechi, members of the lab, and the funding sources. And finally, please stay tuned for the code and the Python library for RNN-PSID, and thank you for your attention.